Okay, so we are going to be looking at theorems and proofs. A theorem is a statement in mathematics that you want to say is true, a general statement about some mathematical objects that you are working with. And typically you will have a bunch of hypotheses, so you'll be saying, if I look at a certain collection of the objects I'm interested in, defined by some conditions on them, then they will satisfy some property. So this will be a statement in the theory of the objects that you're using, and then you will want to give a justification for why anyone should believe this statement. And the way that you do that is you take the basic properties of the objects that you know, that you would agree with anyone else about. You take the hypotheses that you've got, and then you combine them, one thing after another, to move between statements. And the idea is to go from the things that you know, so these properties and hypotheses, to produce a chain of reasoning that gives you your final conclusion, which is the conclusion of the proof. So the way that this is done is by inference, and the basic rule of inference that you need to know is modus ponens, and that says if I give you a proposition A and I tell you, or we know somehow, that whenever A is true then B is also true, then from those two things you can conclude B. And by doing this over and over again, just by combining statements and in this way, you move from A to B to C to D, all the way to, let's say, Z, and where Z is supposed to be the thing you're trying to prove. So that's the basic idea, and it has a very, very long history. This is from Euclid's Elements, so this is the most famous textbook of all time. It is from first written in 300 BC, and it shows you like how sophisticated kind of reasoning in ancient Greek society was. This is in fact a proof of the fact that there are infinitely many prime numbers. And it's written in a slightly difficult way to understand, because the Greeks thought of everything in terms of measurement. So it says, for let the least number measured by A, B, C, etc. have been taken. So that really means multiply all the prime numbers together, which is a step in proving these things. Okay, so so very long history, and we are going to follow in the footsteps of that. So, theorems and proofs. So a theorem is a statement, so a predicate with no free variables, in the theory we are working in. In the theory we have decided to work in. So it could be real numbers, natural numbers, or what have you, differential equations perhaps. Usually start with some hypotheses. Could be let x be bigger than or equal to 0. That could be a sort of hypothesis you might use. And then usually from that you get you'll put down some statement with under these conditions, then something is true. The proof is a justification. The proof justifies your statement, the statement of the theorem. And we do this by using inference. Use inference from hypotheses and basic properties. And sometimes these are called axioms as well. Axioms of the theory. Okay, and the rule that you use, so modus ponens says if I know that phi is true, so if this is true, and I know that whenever phi is true, then I also know that psi is true. From these I can deduce psi. Okay, very basic rule of inference that powers proofs. So, as usual, the best thing to do is to take an example. So let's do that. In the theory of real numbers, the following. There aren't going to be any hypotheses here because I'm going to say something about all real numbers. So for all x, x times 0 equals 0. So this is a nice theorem. So that will be my theorem. And I'm going to go back to the basic properties that I gave in the last lecture to give you the proof. So let me put them back so that we can see them. This is what they were. Just going to use the arithmetic properties of R in order to prove this. And the ones I'm going to use are this one. I'm going to use, so that's additive identity property of 0. I'm going to use the distributivity property, and I'm going to use this one here. So this is the existence of an additive inverse. So the thing that you need to add to any number to get back to 0. So just from these three things, I'm going to be able to prove that x times 0 is always 0. Okay, so we know 0 plus 0 equals 0. Good. And we know that whenever we multiply an addition by something, then we can expand the brackets. We also know whenever a plus b equals d, then a plus b times c, that's equal to d times c. This is equal to a times c plus b times c. So if I now multiply this equation on the right, so putting these two together, I use modus ponens by replacing, I'm going to take a as 0, b as 0, and then c as x. So using modus ponens, we get 0 times x plus 0 times x equals 0 times x. Okay, so I now have to believe this statement about all real numbers. Okay, now I'm going to use another property. So by the additive inverse property, there is some number minus, whatever this is, there's 0 times x, there is minus 0 times x as some real number. And I know that whenever I add it to 0 times x, I get 0. So I'm going to add this to both sides of the equation. So there's another use of modus ponens. 0 times x plus 0 times x. If I add that to minus 0 times x, I get 0 times x, so some number plus its negative. Right? And the whole point of this number 0 minus 0 times x is that it is 0 when I add it to something. So this is going to be 0 on the right hand side, and on the left hand side I'm going to use another property which I forgot to mention, but it is the associativity property. So we're going to move the brackets around. So 0 times x plus minus 0 times x. Well, that gives me another 0. Yeah. So I get 0 times x plus 0 equals 0. And now I know that whenever I add anything to 0 to anything, I get back the number that I started with. Hence, again, 0 times x equals 0. And that was what I was trying to prove. I suppose I could use one more rule if I wanted to just swap these over, the commutativity rule. And so I have finished. And then I put a square at the end just to tell everybody how clever I am and that I've proved my theorem. So that is an example. There are many more examples in the notes. I'm not going to go through all of them, but we'll see many more examples as we go on. So I will leave those till later, and we can also look at the idea of finding counterexamples to theorems and the contrapositive.